Well, thank you for that extremely generous introduction, and I'm really excited to be here. I'm the new director. So there's a brand new thing, the MIT IBM Watson AI Lab. This is a first of its kind, I would say, industry academic collaboration that IBM started. They announced it just over a year ago. It's a $250 million 10-year commitment to fund research, joint research at MIT and IBM. And I'm just going to tell you briefly about what the lab is. And then I thought, because this is a technical audience, I thought rather than giving you a tour of everything the lab does, I'm just going to tell you about stuff that I've worked on and sort of dig into a technical area in depth. But just to start, so IBM and MIT, sort of a natural sort of collaboration here, crossing over this industry academic boundary. And you guys are immersed in this same world. The Vector Institute, all this is very much in the same space. But we're focused around AI in particular in this lab. And IBM Research is a 5,000 person research organization, so we're the size of a small university. And obviously MIT is a great institution here. But this history actually goes way, 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 way back. So the term AI actually came from a workshop in 1955 that was organized in Dartmouth by IBMers who were building the first practical computers, the IBM 701, and future MIT professors like Marvin Minsky and Claude Shannon, who were sort of dreaming about how you would use those computers. So we've been in it together for a very, very long time. And then you mix all of the breadth of academia, and I don't need to sort of sell this to you guys. You know this with University of Toronto being right here. The breadth and the long horizon that an academic institution brings together. IBM Research is big enough that we actually have some of these same functions. We have departments that focus on life sciences, we have physics, lots of these things, but we also have industry problems, we have data, and we have the resources. And in particular, as you guys know, compute resources are a huge problem. It's hard for academic labs to even reproduce some of the results that are coming out of industrial labs these days. So what we wanted to do is really have a deep sort of close relationship where we could be more than the sum of our parts. And really what we're focused on, so there are other parts of IBM that are focused on applied research, but we're really focused on being the tip of the spear for applied research. And we really think that this is the key, these are the key areas that we need to focus on to get to what we call broad AI. So today we have deep learning, it does amazing things, but it has important limitations. So we think that these are sort of areas that we need to focus on if we're going to get AI into every corner of enterprise to serve our customers better. So everything from explainability, so we need to have systems that aren't black boxes that people can trust, that when banks, if you make a loan decision based on a deep learning algorithm, governments are requiring that you explain why. Right, and this isn't a sort of an academic concern. This is a real important regulatory risk. Security, there's all kinds of new security risks that come from AI that we need to be able to work on. We need systems that are unbiased, and that are fair, and that are provably so. We need to be able to learn from small data. People talk about big data all the time, but usually what we're finding with our customers across many, many different industries is even if they have a lot of data, they rarely have enough annotations to drive current deep learning methods. That's a huge challenge that's inhibiting machine learning and AI from getting into every corner of every business. And then finally, we're also working on infrastructure. So IBM's got a tremendous capability both in systems building, conventional digital systems, and I know you guys use some of the very powerful systems that IBM's architected specifically for deep learning, but we're also looking ahead to how analog computing is going to influence deep learning. And just to give you some sense, like by some estimates by the year 2040, if computing keeps on its current track, we'll exceed the power budget of the planet Earth with computing. So not enough solar radiation from the sun, not enough stuff we can dig up out of the ground and burn to keep up with our computing needs. That's even leaving aside Bitcoin, right? And AI is not helping, right? Like we have kilowatts of power just to train a deep learning model. So we're looking at analog computing as a new way to do that. We're also, because IBM's a leader in quantum, we're also looking at ways in which quantum and AI can work together. And one of the projects we have is actually with Peter Shor, who invented Shor's algorithm, looking at how AI and quantum may or may not interact with each other. So we have a very broad portfolio of these areas really focused on how do we just knock down these barriers to getting AI into lots of different places. But what I'm going to talk to you about today, again, because rather than giving you an overview, this is a technical audience, I wanted to really dig into something specifically that I'm working on. And one of the themes that we're building in Cambridge, so we have a new lab in Cambridge, we just spun up, we were 20 people at the beginning of the year, we're 60 people now, we're going to continue growing right in Kendall Square, right next to MIT. And we're building a small group that's working on issues that are close to my heart, which is looking at how neuroscience and AI may or may not interact with each other. And the idea here being that our brains are the kind of the one existence proof in the universe that we know of that can do the kinds of intelligence that we want. And we want to ask, is there any crosstalk? Are there ways that we can be inspired by neuroscience to build better deep learning models? And are there ways that those deep learning models could even perhaps help us understand our brains better? And this is going to be mostly work done by my first graduate student that I graduated, Bill Lauder. And this is work we've continued since I've joined IBM, which is just 6 months ago. I should say I'm a recovering academic. this is my first real job, just to be clear. So it's an interesting journey. So this is basically it. Right, so we call them neural networks because there are neurons. So the thing in green is a fluorescently labeled cell. That's the neuron. And then the things that are labeled in red are what are called synapses, the connections between the neurons. And so brains have neurons and synapses, and artificial neural networks have units and connections between units. So that's the first piece of the inspiration. The second piece of inspiration is this notion of depth. Right, so we know that we've known for a long time in the brain that we have this hierarchical deep organization where information comes in through the eyes, but then it goes to successive processing areas in the brain. So what you're seeing there is the brain of a monkey. And visual information in cerebral cortex, which is the outside part of the brain, goes from areas that have names like V1, V2, V4, and there's this successive deep processing. And this helped inspire, arguably, some of the idea that there's this deep processing in the brain. And there were models that predate deep learning, like things like Fukushima's neocognitron and other models that were sort of inspired by this idea. But this is really all we've got so far, right? So I wouldn't claim that deep learning has deep biological inspiration at this point. So what we wanted to ask is, can we go back to the brain and, is it a worthwhile exercise to try and squeeze more inspiration out of the brain? And then in turn, can practical deep learning models help us better understand the brain going back the other direction? And can we have a virtuous cycle there? And if you haven't been following the neuroscience literature, it's a surprising thing happened over the last few years, which is that it turns out that deep learning models are better models of the brain than any model that was designed to be a model of the brain. So computational neuroscientists have been building bespoke models of the brain for a long time. And some of the models are these models like here, and some of these papers are even my papers. But it turns out if you're fitting the neural responses of actual neurons in a brain. So what this is imagine a monkey with electrodes in its brain. So you're wiretapping the activity of units. And then you're showing it different images. And there are these funny images where you have objects appearing in different orientations on different backgrounds. Each one of these points along here is the response of a neuron to a different image. And what you see here is okay, this neuron had response to different things. They're sorted by categories. So this is the category of faces. You'll find that neurons have particular response profiles. People have been trying to build models to explain what it is the neurons are doing for a long time, but it turns out if you just take neural networks like AlexNet or Inception or whatever, they actually provide a much better fit to the actual neural data than any model that any neuroscientist dreamed up. So it feels like there's some sort of connection here that just by solving the problem, you're getting closer and closer to actually maybe explaining the brain. So there's an idea that's emerging that, well, maybe the brain's doing something like deep learning, and maybe that's fine. That just says, okay, well, we can just leave the brain aside. We already understand it. It turns out it's deep learning. But the other position is, well, maybe there's a closer overlap that we could start to work with. So, and it turns out that as time has gone on, as the models have gotten better at these are ImageNet trained models at solving ImageNet. More and more, they do a better job of explaining the population activity of the brain. So this basically on the y-axis is how much of the variance does it explain? And then here is basically time. As models have gotten better and better at solving ImageNet, they're better and better at explaining the brain. So maybe this is it. Maybe the brain just does deep learning. And there have been headlines. This came from work that my PhD advisor did. So machines finally match monkeys and key image recognition tasks. Maybe the field of neuroscience is done. The answer is just deep learning. It turns out that that's probably not the right answer, and I'll tell you why. So one thing is, all that was collected with static images, and our brains are keenly attuned for dynamic data. And I think video and deep learning and dynamic data and deep learning is just starting. And when you look at images like this busy street scene, there's lots of things going on. There's this constant churn of moving content. Many of the things that you can recognize, you actually don't have pixel level information to recognize them at all. These are faces, these are people, but at a pixel level, if we crop these out, there's actually no information that would tell you that. So there's something about how our brains are very much attuned for dynamic information. And if you actually spend any time recording from the brains of monkeys, which is something that I did in my youth, I spent 5 years working with monkeys, putting electrodes in their brains, which was kind of a weird thing to do in retrospect. But it turns out that the first thing you notice is if you show a static image to a monkey and you record from a neuron in its brain, you don't get a static response back. So if you take a convolutional neural network and you put a static input in, you'll get a static output. There's no notion of time in a convolutional neural network. Whereas in a brain, you get this interesting response where if you present a static stimulus, like this image of a monkey face to a monkey, you get this funny little brief transient response, and then maybe you get a little bit of modulation, but largely suppressed responses. And it turns out the only way you can get a sustained response from the neuron is actually by showing it a moving stimulus. So there's something qualitatively different about what the brain is doing relative to what, say, a convolutional neural network is doing. And it gets even more interesting than that. So it turns out people have done experiments. This was done by Carl Olson at Carnegie Mellon University. If you show animals sequences of images and you give them lots of pairings, so if you show them the monkey image A4 followed by image B4, show the sequence many, many, many times. So B4 always follows A4, and B5 always follows A5. If you then later go in and record from neurons in the monkey's brain, you find that the neuron responds to A4, but it doesn't respond to B4. And it responds to A5, but it doesn't respond to B5. So this leads to the idea that, okay, well maybe, it could be that just that they picked a neuron and it just happens to like A5 and A4, it doesn't like the B ones. But it turns out if you take that very same neuron and you show it a sequence that isn't, where the sequence isn't violated, that doesn't match what happened during training, the neuron actually does respond robustly to B4. So something about the brain is constantly tracking temporal statistics and correlations in the environment, and this is something that our current deep nets aren't yet capturing. And of course, we still have a long way to go in deep learning. Deep learning is doing amazing things. Here are examples in computer vision that when I started doing computer vision back in the early 2000s, before deep learning, these tasks seemed unthinkable to me. The idea that you could have an image and get these amazing captions. This is from Andre's work with Feifei. Captions like a man in a black shirt is playing a guitar, construction worker in orange vest is working on the road. But when you dig deeper, into these models, you discover that actually they're missing a lot that's there. So here's an example that Josh Tenenbaum and Sam Gershman at MIT and Harvard respectively came up with, where they took those very same models and they showed images like these. So this is a man riding, this is the very same captioning system, a man riding a motorcycle on a beach. An airplane is parked on the tarmac at an airport, and a group of people standing on top of the beach, which is true. This is a good caption. This is actually an accurate caption. So there's a sense in which, even if we're doing these supposedly superhuman things, we have a long way to go in terms of extracting this structure. The other problem is that all of these ImageNet trained systems are trained on ImageNet, millions of images. And when my daughter learned what a cat and what a dog were, I didn't show her thousands of flashcards. We get almost no supervised learning in our natural existence, and yet we're able to do amazing feats of few-shot learning. So here's an example. Does anyone know what this is? Okay, we don't have any electrical engineers in the audience. That's good. So okay, even though you've seen this once, only one example, you're now experts in that object, whatever it is. So I can ask you, is there one in this image? Yep. How many in this image? 2. Is there one in this image? Yeah, but it's kind of weird, right? So even with just a single example, we're able to extract, become experts instantly in one-shot learning. And we're even able to reason about the object when the input doesn't match our expectations. So this is very different from what our current generation deep networks are doing. Here's some other examples, of things we're able to do. So ImageNet doesn't include, it turns out, any fur-covered flatware and dishes and things. We're perfectly able to reason about this and say, okay, that's a cup, a saucer, and a spoon, but it's weird. If you give this to state-of-the-art superhuman ImageNet trained systems, the most common response I get from all of the leading vendors is teddy bear. This is very not a teddy bear. This is actually a piece of artwork that's in the Museum of Modern Art in New York called A Luncheon in Fur. Also, there's interesting phenomena where even these supposedly superhuman systems, if you even just include objects out of context in the wrong places and you occlude, they'll suddenly start making egregious mistakes. So even though it gets bird correctly when the penguin is in isolation, it thinks it's a cat and it mislabels other things if you just put other objects nearby. So something is radically different even in these superhuman trained ImageNet systems. It should be said, the whole superhuman ImageNet thing, if you don't know, it's just because there's so many dog breeds in ImageNet. It's really hard to know enough dog breeds to get all of ImageNet right, but something is deeply wrong. So a thing that we're working on and we're very interested in, that a lot of people are interested in, is this notion of unsupervised learning. So we're clearly not getting supervision. Current systems require that supervision, and they're also fragile, and they're not extracting the structure in a deep way. Maybe what we're missing, and Jan LeCun has this cake that you may have seen that he presented at NIPS a couple years ago, with the idea is the bulk of machine learning might be unsupervised learning, and things like reinforcement learning and supervision are just sort of icing and cherries on the cake. We very much believe that same idea. But coming from a neuroscience perspective, one thing that we got really interested in is this idea that oftentimes the world tells you its structure through temporal evolution. So the world, if you watch, I'm going to have a lot of examples from video, but everything I say here applies equally well to stock market data, to other kinds of multivariate time series data. This idea that if you just simply watch the world evolve, it tells you something about the structure of the world. So we watch a tennis serve, not only do you get information about how shadows move on objects and the sort of inverse EM of vision, you also get ideas about how your different actors are articulated, how they fit together, how objects interact, like the ball being hit, so the physics of the environment. So there's a huge amount of information that's there if you just watch, and you're sensitive to these temporal statistics over time. Now, brains are very sensitive to these temporal statistics. So I showed you one example with that sequence learning task. Here's another example I like where this is an experiment by Guy Wallace and Heinrich Bühlthoff, where they showed these rendered faces and they would just rotate, and they showed people passively these rotating faces. Interesting thing is, if what they did in the experiment was, as the face rotated, they actually just morphed it into a completely different face. And they had subjects watch this, and by and large, the subjects didn't notice that this was happening. But then if you ask them if these two are same or different, after watching many temporal sequences of this morphing face, they would incorrectly associate the frontal face with the wrong morphed face in a way that they wouldn't if they hadn't seen those sequences. So it's as if your brain is constantly watching the statistics, and even if you're giving anomalous statistics that would never happen in the real world, you just sort of soak those up and you do the wrong thing. And one study I did, sort of one of my only human studies that I did when I was doing my PhD, you can actually even do this in more dramatic ways, where if you track people's eye movements, you can flash an object up in the periphery, and then while your eyes are moving to it, we make ballistic eye movements called saccades, and you're completely blind while your eyes are in flight. So if we have fast enough closed loop control, we can actually swap the object for a different object. So when the object appears in the periphery, you try and move your eyes to it, and by the time they get there, it's a different object. And we can actually trick people into thinking that an object looks different when it's in this part of the visual field than it looks when it's in the center of the visual field, and people will actually make consistent mistakes. So your brain is just constantly soaking up these temporal associations. We have all kinds of evidence that's happening, but we don't have a mechanism yet in our deep net models that has this property. And now people have thought about ways of incorporating temporal information. This is a notion of slow feature analysis, where slowness, where this came from Terry Sinofsky and Lawrence Wiscott, this idea that maybe you're trying to extract signals that vary slowly in the environment. Like if you look at any given little aperture of pixels as I'm moving around, they vary a lot very quickly, but the actual presence of me as an object is relatively stationary. I don't teleport away and then teleport back. So they've been trying to extract these slow features. This has been an influential idea theoretically, and it's popped its head up briefly in computer vision and deep learning from time to time, but it really hasn't quite caught traction. So we wanted to look in particular at this notion of prediction as an unsupervised learning rule. So basically the idea is, can we self-supervise systems by watching video and capturing these temporal signals purely by doing prediction? And I'm going to argue that brains are particularly adept at prediction. In fact, that your entire conscious experience may be a prediction right now. So does everyone know who this is? Who is this? Serena Williams. Yeah, I don't know how audiences know this, but it's not Venus, it's Serena. So that's Serena. She's doing a tennis serve. Serena's tennis serve is 207 kilometers per hour. That's 57 meters per second, which means the ball traverses the court in 400 milliseconds, 4 tenths of a second. Now, it turns out that the time it takes from photons hitting your retina to actually getting to the cerebral cortex is about 60 milliseconds. So the ball's traversed 3 meters on the court in the time it took just for the information to get through there. Your brain's actually incredibly slow. And then to get all the way through the entire deep network of the brain, this deep processing, takes about 170 milliseconds in a human. So the balls travel 9 meters in that time to get through the whole deep net of the brain. So if you think you saw the ball when you hit it, you couldn't have. You saw a prediction of where the ball would be based on the wind-up of the serve. And okay, so here's an illusion, a classic illusion that illustrates this prediction phenomenon. So this is called the flash lag effect. So if you look at the center point, and you look at this clock hand kind of moving around, there's a flashing bar. Does the flashing bar look like it's lined up with, in front of, or behind the clock hand? Behind, right? And of course, it's an optical illusion. So the rule of optical illusions is if it looks one way, it's actually the other. So this is actually perfectly lined up. And what's happening here, the classical interpretation here is that because the clock hand is predictable, your brain just puts it, you perceive it where it really is right now, canceling out the pipeline latency of your brain, whereas the flashing bar has to go through all that extra latency, so it ends up appearing behind, right? It's lagging because you can't predict where it's going to be. And it's also additionally, do people see that it's kind of tilted? It's kind of weird, right? And there's not classically a good explanation for why it's tilted, but I'll show you why it's tilted a little bit later. Okay, so we wanted to see if we could take inspiration from what we know about the brain and build that into deep learning. So we ended up getting into this field of future frame video prediction. So basically the idea is if you see a sequence of images conditioned on that sequence, we want to be able to predict what the next frame is. And at the time, this was a relatively young field when we started this work. But now future frame video prediction, generative models, predictive generative models is a thing. There's dozens of papers now about this. But as we were wading into it, there were about 5. So we did, when we started, we wanted to do just the very simplest thing, and this was published in iClear back in 2015. We basically took an autoencoder, and then we stuffed an RNN in the middle, because obviously a recurrent neural network, so can keep track of time and can do this sort of predictive modeling. We also, it turns out back in 2015, we jumped on the GAN wagon really, really early, and we had it turned out to be one of the earliest papers using GANs. Now GANs, of course, are everywhere, and that's amazing, but we had an adversarial discriminator in there as well. And then what we found is that, this is hardly surprising today, but back in 2015 or 2014 when we were starting this work, we were shocked how good networks were at predicting what the next frame would look like. And at the time, we were using these very simple rendered sort of faces because we could control the rotation. And we found, we could predict, as faces rotated around, we could predict what they were going to look like in the next frame. And again, these are generative networks, so you're effectively rendering images, out of nowhere. But the key thing that we were interested in is, would doing this predictive modeling help you do unsupervised learning? So again, we're aiming for getting fewer shot learning, ideally one-shot learning. Does being able to just do this prediction and seeing lots of these video frames, can we use that to build better representations of the objects? Basically the idea being, if you can predict what the next frame looks like, you're being forced to learn things about the structure of the object, how objects move, how light interacts with objects. So what we ended up doing is just something very simple, which is we trained these models, we sort of cut off the decoder part that was rendering, and then we just peeled off the features from the RNN and put them into a very simple supervised classifier and asked, could we use the representations learned in an unsupervised way to do semi-supervised learning for another task. And so here's a classification of these faces, and what we found was, again, this wasn't trained to do recognition, the representations weren't trained for recognition, but if we train them in this way, we could outperform. So the blue line is this very simple predictive generative network that we built, could do better with less examples. So you kind of want to go up and over if you're doing more with less data. So we found that this kind of pre-training with this predictive supervision was helpful for doing subsequent recognition type tasks. I was going to cut through a few of these things, but ultimately, so that was a little bit of a taste of what these things were like. But what we're really interested in going is really taking this idea further from neuroscience, this idea of predictive coding. And the idea of predictive coding is that maybe the thought is maybe one of the key principles of the brain is that the brain is constantly predicting its own activity. So this idea was popularized in 1999. It's an old idea, and here's the basic gist. The idea is that inputs come in, and then you make a prediction of what the input is. You cancel that out, and then you only send forward the errors relative to your prediction. So this was originally cast as like an efficient coding idea. So the idea would be like, hey, you just want to send fewer action potentials or something, less energy or something. So we want to just efficiently, compress the signal. And what we wanted to do then was to take that and sort of take it to its logical deep learning, bring it into the modern world of deep learning. So we built this. So what this is, just to walk you through it, is, so this is the repeating element. So we've taken what we were doing before, which was just an autoencoder with an RNN stuck in, and we made a recurrent module that we could repeat and stack. So we have an input come in, go through a convolutional layer. There's a prediction. We subtract the prediction pointwise, and then we send the errors forward to the next level. And then we have a recurrent neural network that's kind of keep track and make a prediction of what the next frame is going to be, conditioned on the previous frames. And then each layer sends feedback from the recurrent layer down, so it can make better predictions from hierarchical data. So if you look at this arm is a straight up convolutional neural network. So on time step 0, if there were no time, this would just be a CNN, which is good because we know that CNNs model the structure of what the brain does very well. And then it's also a generative network. So if you put stuff in up at the top and you just let the network propagate, it'll render down into an actual image that you can look at. So this is kind of a nice, you have an analysis and a synthesis kind of arm, and it can be trained end to end entirely on the error. So we just want to minimize the error. Very, very simple setup. Just train the whole thing end to end, minimize the error. Okay, so we called these predictive coding networks, and as all of you being deep learning experts know, this is a terrible name. This is unacceptable as a name for a deep network. So we thought deep prediction, no. Predictive, no. BillNet, it was made by Bill Lauder, no. I can't believe it's not AlexNet. And we ended up settling on PredNet as the answer. So this is a good and solid name for a deep learning thing. And for better or for worse, this is now stuck. So this is now called the PredNet. That's fine. And what we found is that we started with these synthetic images, and in the earlier case we could only really get it to work with 1 degree of freedom. We just had faces that could rotate about one axis, and then when we tried it with the PredNet, we found that we could have faces that were tumbling. So the way these plots look, this is the predicted frame, and we just time shifted it. So this is the actual sequence, and then what's below here is the prediction of what the next frame was going to look like before it actually happened. And you can see that after it kind of locks on, it kind of doesn't know which way the face is going to move, but then it locks on, and you get a pretty good prediction of what the face is going to look like. So that was all fine and good. And we could do things like we could decode parameters of the object from the RNN layers. This is again the idea that we're doing unsupervised learning. So we want to be able to extract principal components of the face. We want to be able to extract things like the angle and the speed of rotation and things like that. We could also do this face recognition thing where we peel off the features that the RNNs learn, and then we can show that as a semi-supervised learning method, we could outperform things like ladder networks and other sort of state-of-the-art. We're not making a big deal about the difference here, but it's at least on par with sort of standard semi-supervised learning methods. So we think there's some legs to the idea that learning to predict is a good way to learn how to represent the sort of like the actual structure of the images. Of course, those kinds of synthetic faces aren't, that's not terribly satisfying. Everybody's interested in autonomous vehicles. So Bill started running this on car-mounted camera data, because that's where the money is with the auto companies. And so this is video. We trained it on Kitty, which is a data set of somebody driving around in Germany. This is the Caltech pedestrian recognition data set. So this is somebody driving around Pasadena. This is what we tested it on. And it turns out these networks actually scale beautifully to actual real-world data. So what you're seeing down here, it looks like a blurry version of that, but this is actually a future frame prediction of what the frame would look like before it happened. So it's a little bit blurry, but some interesting things you can see that the network kind of implicitly learned about the world. So one thing is, you notice as this car drives by, the network knows that it needs to re-infill road behind where the car was. This whole edge is being confabulated in real time, so there's no information about what's over there, but it's making reasonable predictions. If you look at these shadows, it knows something about perspective. It knows the shadows have to expand as they come closer. It knows that things are far away and move less. So there's implicitly built up in this network, it knows a lot about the structure of the world. It also knows things like, it knows that when one object passes another object, it has to occlude it. And then when the object passes by, it knows that it needs to re-infill road behind it. So just simply by having this dead simple, kind of dumb prediction, loss and training end to end on lots and lots of data, and the supervision is for free, right? Because you just make a prediction, the world, then the future arrives, and you compare your prediction to the future. You can get arbitrary amounts of training data, and then you can learn these kinds of representations. And again, the idea here is not just, sorry, question?
I was just wondering, how far in the future is it predicting these things?
Right, so in that frame, so in that example, it's 100 milliseconds into the future, a tenth of a second. We can go all the way out to 10 frames out in the future. The predictions get blurrier and blurrier as you go out into the future. I don't know if that's a feature or a bug, because the world becomes less certain as you go farther out. And we can talk about whether this should be probabilistic. It should, and it's not, but we can get interesting mileage out of this this simple deterministic framing. But the idea here was actually what we really want to learn is information about the structure in an unsupervised way. So we took the PredNet, we trained it on car-mounted camera data, and we took a data set from these guys, Comma.ai. So these guys, this is George Hotz, the guy who hacked the iPhone, and anyway, he has a self-driving car company, and he's like poking everyone in the eye. They made a data set of car-mounted camera data with the steering telemetry. So we asked, could we just, purely by learning the prediction of the next video frames, could we then do semi-supervised learning to predict which steering angle the car should be turned to? And they built a supervised CNN to do that task, and that's what's here in red. The ground truth of the actual steering angles is in black, and the PredNet, which is again just trained on video prediction, and then a very small amount of supervision to map it to regress it against the steering angle. You can see that the PredNet actually learns really well to predict not only what the next frame is going to look like, but you can actually predict where you should turn the wheel to make that happen. And it turns out that with less data, you can. So these are the Comma CNN models. With the PredNet, you can actually outperform a bespoke supervised model. So whether this will be useful, down the road in self-driving cars is an open question. We actually do have a startup that does this, but it suggests again that there's sort of legs to this approach. You might also ask, can it only do things it's seen before? And we sort of went through an exercise of showing it other objects that are completely different than what it's seen before. And here's an example where it does a semi-decent job of something that's very far out of set and generalizes to this sort of top object chain rotating. This is one that was trained on faces, but we tested it on one of these coil object sets. And you can see sometimes it doesn't always work. Like here it's trying to turn it into a face. It's sort of this like Edvard Munch kind of scream. So it doesn't always work. But if you train it on a diverse set of different things, we found that basically the PredNet could learn to rotate or sort of move almost any object. We've also done things like having balls bouncing off walls. It can learn rudimentary physics and things like that as well. So the code for this is available online. It's been started a bunch of times and forked a bunch of times. One of the other interesting things that we've found people using it, a lot of people using it for robotics, but this was one I liked because it was an actual real world application somebody was using it for. If you integrate over the error units in the network, it tells you how surprising the next frame is based on things it's seen before. So you can use that for anomaly detection, right? And I think this is a good application for PredNets in general. We sort of foresaw this and we mentioned it in the paper, but we didn't actually do anything with it. These guys were using it for factory monitoring, so automated factory monitoring. So this is a video where they're showing the error units integrated over time, and what happens here is like shit goes sideways and like stuff starts falling over in the factory and people start running, and it nicely predicts like something is out of the ordinary. So if you had a system that could sort of alert the authorities automatically, that's what this kind of thing could do. And you could imagine doing that same kind of anomaly detection for any kind of network intrusion or predicting financial data that something weird is going on. So that's an example of us going from brain inspiration to something practical in deep learning that we can actually use for lots of different applications. Having a foot in the world of neuroscience, we also wanted to ask the other question, like, okay, now that we have this model, can this help us understand the brain better? Because if we can get that loop going, then maybe we can make progress even better. So there's a number of things that are true about the PredNet that match up in interesting ways with biology. So one is that neurons in early visual cortex have this oriented bandpass structure. They're like Gabor wavelets in their receptive fields. Now this also happens, like every neural network that's trained on ImageNet has these sort of receptive fields in the early layers that have this property, so that's a nice match to biology. PredNets are no different. But the interesting thing is there are a lot of features of biology that weren't previously well explained by deep learning, but now with the PredNet are. So this is one of them. So I showed you that when you present a static image, you get this dynamic response, this sort of willfully dynamic response to static inputs, and the PredNet does exactly that, and it's easy to understand why. It's because when the image first appears, it's surprising, and the network can't predict it away, so the activity flows up through the feed-forward path, but then as it learns to predict it, because it's there and it continues to be there, it goes down. You also get off responses, which is something else that you see in neuroscience, where the neuron responds when the stimulus goes away. And again, that makes perfect sense with this sort of surprise framing. There's also all these effects that you find in neuroscience which are kind of surprising or interesting to neuroscientists, where if you take a bar that's oriented in the preferred direction for a given neuron, as you make the bar bigger, the response goes up. But then as you make the response bigger than its classical receptive field, the response tends to go down. It's suppressed. And this phenomena also just comes out naturally of the PredNet. The basic idea being that if the neighbors of that neuron can predict what's inside that area, then it just naturally suppresses. So these are phenomena that just naturally fall out. Same thing with something called surround suppression, where as a dot gets bigger, the response gets larger until a certain point, then it gets smaller. And it turns out if you turn off different brain areas, like you can put a cooling coil on a brain area and deactivate it, some of these effects go away. And because we have full access to the network, we can actually perform all of these same neuroscience experiments, but on the deep net instead. And we find exactly the same pattern where it's this suppression is coming from a top-down sort of feedback connection in the brain and in the neural network. This effect with sequence learning, that also happens with PredNets. If you look at the PredNet internal representation, you can see why it's happening. It's learning to make this transition so that when you're presenting the stimulus that can be predicted away, the PredNet doesn't need to respond because it's already predicted it away, and it's already part of that response. Whereas if you show it in a sequence that's unpredictable from past training, you get a robust response because it's surprising again. And we actually trained this with exactly the same number of repetitions. So the monkey saw 800 repetitions of the sequence, and so did the PredNet, and the PredNet picks it up exactly at the same rate. Kanitsa figures. So these are classic examples of illusory contours, where if you have these little Pac-Man things lined up the right way, even though there's no line here, you perceive there to be like a square, right? As you perceive this. And it turns out the PredNet sees that too. This is a complicated figure, but it turns out it sees it and also has similar time dynamics for responding to that edge as neurons in your brain that respond to that edge even though there's really no edge there. And then finally, you might also ask, I showed you that flash lag illusion, which was like a classic example of a predictive illusion, where you see the bar where it really is, and then this flashing line appears lagged and also tilted. And it turns out, because this is a generative network, we can just see what it sees. Like we can just look at the error representation, and we can see what the PredNet is seeing. And what you see is that, in fact, the PredNet sees the flash lag illusion too. Now, here's a caveat. You're actually seeing double flash lag illusion here, because you're seeing the PredNet's flash lag illusion plus your own flash lag illusion on top. So for us to see just one, I have to stop it. And we have to look at it frame by frame to verify that it works the same way that your brain works. And here it is right there. So the bar is not only lagging, it's actually tilted. And again, nobody really had a good explanation for why it was tilted, and we still don't. All we know is that the PredNet sees it that way too. So we see it with this tilt. Actually, the angle is almost exactly the same as we see when we look at this illusion. So it feels like maybe there's smoke, maybe there's fire there too. Like I'm not saying that the brain is a PredNet, but maybe there's a sense in which the PredNet's a lot closer to what the brain's doing than what just a straight CNN is doing. The other fun thing is once we put this out there, so a lot of people in robotics picked it up and did interesting things with it, but a lot of neuroscientists picked it up as well. So a group in Japan actually looked at it with these static motion illusions. So the way these work is if you look at this, even though this is a static stimulus, you perceive it to be rotating. So these are kind of maddening illusions if you look at them too much. And if you change it, there are versions that don't have illusions. And again, it turns out even though this is a static stimulus, the PredNet sees a motion field the same way you would see a motion field. So even though the stimulus is not moving, the PredNet kind of feels like it's moving if you actually look at the optic flow inside the network. So again, all kinds of evidence that something similar is going on across these two networks. How am I doing on time? Cool, we're close to the end. So just one other thing. I mean, if we really want to close this loop, ideally we would be able to go all the way back to experiments that could happen in animals and do new neuroscience experiments. So one of the things we notice here, again, this was us reading out the steering wheel angle. Along the way we thought, okay, well, surely we should, if you had access to that information about where the steering angle was, you should be able to make better predictions about what the next frame will look like. Because if you know the wheels are turned, you should predict, it should improve your prediction. So what we started doing is plumbing in that telemetry information into the RNN part of the PredNet to see if we could improve the predictions. In neuroscience, this would be called an efference copy. It's like a copy of the motor signal that's giving rise to the behavior. And what we found was, not surprisingly, if we give the PredNet extra information about what the car is doing, like what's the steering angle, what's the brake, what's the throttle, we can get much better predictions. We converge faster, and we get better quality predictions of the world. You can also do interesting things like, what if you condition on counterfactual steering angles? Like, what if I turned the wheel a way that it didn't turn? Could I predict what the next frame should be based on a different steering angle? So that's kind of a fun little variant on it. But because of this, we thought, okay, well, if this works for the PredNet, maybe this works for the brain as well. So Greg Guichons was doing animal experiments and found out about this work, and actually did this experiment with an actual animal with an actual brain. So he took a rat that had electrodes implanted in its brain, measuring an accelerometer on the head, and the idea was there was a prediction that there really ought to be motor efference copy signals going into, if the brain's doing something sensible, it should do the same thing the PredNet does, and you should just plumb these signals right into the predictive network to make better predictions. And it turns out that even in the dark, so he was able to sort of demonstrate these connections exist by showing that even in the dark, in visual cortex, you could actually decode which way the animal's head is pointing, which is consistent with this idea of doing this predictive learning. So we're starting to close the loop between things we can learn in deep learning, get inspired by neuroscience, improve our deep learning model, better model the brain, and then actually maybe even do experiments that can change our understanding of how that works. So we think this is an interesting nexus. I mean, it's certainly not the only answer. I mean, we can get inspiration. We should get inspiration from all sources, statistics, physics, whatever. It's not like we should just copy the brain because the brain is the brain and that's the only way to go. But we do think increasingly, because there's this better and better tools in neuroscience, there's this kind of loop that we can really start to exploit. And then just to tie it back to things we're doing now in the MIT IBM lab, one problem with this is that while I can predict the next frame of what I'm going to look like at the pixel level over very short timescales, and this gets to your question about how far in the future can I predict, I can also make predictions about other things. Like for instance, I can predict that many of you will go out of this room and go and have lunch, and I saw there was a Tim Hortons downstairs and stuff, so I know all kinds of things about you, and I can make predictions about future states of you, but I can't predict the pixels, right? The pixels is the wrong representation in which to be predicting those things. I can predict things about where you'll be, properties like that, more like symbolic ideas. And this is something we're actually really interested in the lab. We're working with Josh Tenenbaum's lab on can we actually merge neural networks to more symbolic representations and then think about doing predictions in those symbolic spaces rather than doing them in purely sort of pixel level distinction. So here are some examples of things that are hard for neural networks to do today, like answering questions like how many blocks are on the right of the 3-level tower, or will the block tower fall if the top block is removed. At a pixel level, I probably couldn't predict which way it's going to fall, but if it's going to fall, I know things like it's going to fall, which is more of a symbolic idea than necessarily a pixel prediction. So one of the projects that this is one of the first papers that's going to come out of the lab. This is going to be an oral spotlight paper in NIPS this year in December. Collaboration between Jiajun Wu and Josh Tenenbaum at MIT, and then Chuang Gan, who's in my group at IBM. Solving this Clever data set. So what Clever is a series of rendered objects like this, and you have to answer questions like how many cubes that are behind the cylinder are large. And humans have no problem with this. This is a very easy task, but training an end-to-end neural network to do this is actually quite hard. And what's interesting about this, and why it's a NIPS spotlight paper, is that basically what they're doing is they're fusing neural networks. So a vision component is a CNN, using an RNN for language, but then what the RNN is doing is seek-to-seek translation from a sequence of words in a question, but not outputting a sequence of other words or outputting a label, but instead outputting a series of symbolic operations. So parsing the question into a symbolic program. And then what the CNN does is create a structured representation which is fundamentally symbolic, and then a program which can then be executed on that symbolic data. And when you do things like this, you end up getting, where Clever was hard to completely solve, by decoupling the actual perception part from the reasoning part, you can actually just completely solve this. So they're up to 99.8% accuracy without having to do huge amounts of supervised question answer pairing. Of these inputs. So we think that thinking forward, if I want to make predictions about where you're going to be, even make predictions about where you're going to be in a year. It's like you're probably going to be working in a job in AI, or maybe you're going to be here still. Like you can make all kinds of reasoning about that, but really the representation is fundamentally different than the kinds of representations we typically deal with. So we're very interested in merging all of this work together. So with that, I'll close. I just want to thank all of the folks who funded this work while I was still in academia, particularly Bill, and various funding sources. And of course, now that we brought this work to IBM, I'll thank my own company for funding it. That's kind of a weird thing to think about. And of course, I also want to thank you guys for coming out and taking the time to listen, and for inviting me and for showing me around this awesome office. Thanks.